Okay, good afternoon, everyone. Hopefully you can hear me okay. Thanks for coming. My name is Scott Martin, and I'm the sales director of Glencore Technology based in Vancouver. And our really exciting webinar today is called Maintaining Your IsaMill, and we're just going to get started right now. But while we wait, just a couple of quick housekeeping items. Today's webinar is about the IsaMill. There will be a Q&A button at the bottom of your Zoom screen, so you can send in questions. And if we don't have time, like the previous one, to answer all the questions, they will be answered and emailed to us, to all of you afterwards. You can ignore the raise hand function during the webinar unless you have an urgent technical issue or something that you want to alert us to. It will be recorded, and with the questions, we will send out a link where you can access this webinar later on. If you like, you can minimize or change the presenter thumbnail. All you do is click on the screen and tap through the different viewing icons to what you like. So the webinar today will start with a really exciting presentation, lots of great visuals to discuss the IsaMill and the recent developments in its design. And then we have a very experienced panel of experts from our projects and engineering group, aftermarket maintenance, really the brains of the operation at GT. And they'll answer some of the questions you have. Some have been submitted with your registration. And again, if we don't get to all of them today, we will email a list of the questions and the answers. So this is a great opportunity to get the guidance that you need on your mill, or if you're working on a project where you're considering an IsaMill, some information there. So our presentation today is by Ion Gurnett. Ion is a senior metallurgist in the mineral processing team. He's worked in both projects and operations for the last 10 years. He started out at Glencore's Mount Isa Mill, or Mount Isa mine, and he worked at Tech Red Dog, where we now have the M15,000 IsaMill, and is now working with GT, primarily focused on the IsaMill. So with that, thank you for attending, and I'll pass this over to Ion.
Thank you, Scott. No worries. So like Scott said, this is a quick presentation to help discuss a bit of the IsaMill technology. I would encourage you to write down any questions throughout the presentation and really take advantage of the opportunity we have with our technical experts in the maintenance, aftermarket, and E&I fields. So with that, let's start the presentation. Glencore Technology does produce 5 core technologies, 2 in the mineral processing space, the IsaMill Jamison cell, 1 atmospheric leach, the Albion process, and we have a pyro process, the IsaSmelt IsaConvert, and IsaKid, which is the electro-wind facilities up in Townsville. Today's focus, we're going to specifically talk about the IsaMill and particularly the maintenance aspects. So parts, development, new materials, and really have that open forum and discuss any questions that have been bothering you or anything that you're potentially interested in. So with most presentations, I always like to start with a bit of a safety share. And today's is working at heights, and it coincidentally feeds into one of the benefits of the IsaMill. In some stirred milling plants, working at heights is a potential risk and a potential danger that you have to think about when performing regular maintenance tasks. One of the benefits of the IsaMill is it's intrinsically safe, and it's a horizontal milling layout. This means you don't need to work at heights. The entire mill is accessible from the mill floor, and there's no need to work under suspended loads. So, like I said, something to consider about when performing regular maintenance duties. Now, what are we going to cover in this webinar? And we'll go through these main key items. I'll do a bit of a refresher on how the IsaMill works from a process perspective, do a description of the maintenance components. So those that aren't too aware of the technology, they can see all the key aspects and really see how simple the layouts is and what we have to do. We'll go through developments and maintenance practices. So some of the let's say cool work we've done with materials, maintenance, layouts. How we'll do a run through a very quick little video showing you how the maintenance is conducted for those that are curious. And like I said, it's a very simple process. And to me, the highlight of the webinar is really that technical discussion and any questions that you may or may not have. So with that, let's get underway. So let's talk about the mill. Those that don't know, this is effectively the layout of an IsaMill. We pump slurry in at about 20% solids by volume at about 50 to 150 kPa. This slurry enters this closed vessel, which has a series of discs on a fixed speed shaft and volume filled with media. These discs are rotating one way, and as I said, they're on a fixed speed and they have a tip speed of around 20 meters per second. This speed creates a highly agitated environment, which then agitates all this ceramic media that we have inside the mill. The mill is typically filled between 60 to 75% with ceramic media by volume. And what this does is it creates these highly agitated zones between the discs. The high centrifugal forces inside the mill will force media towards the front of the mill, so your slurry has to pump through it, so there's no short circuiting, and it will retain coarse particles within the mill. I.e., if it's coarser, then only fines will enter the mill disc and that yellow rotor. You'll notice the gap between the disc and the rotor is quite small. This is quite clever. This is quite clever. And what it does is it creates hydrodynamic forces that will push your slurry out to the edges, then pump back towards the front of the mill. What will happen there is as your those streams will push keep the course up towards the front of the mill, and your fines will pass straight through. One of the things that's really worth mentioning is the actual feed size of the mill. We can take a whole variety of feeds, and the really thing that dictates that is your media selection. Currently, with 6mm media, which is one of the largest ones we've tested, we know that the IsaMill can feed about 300 to 400 microns with a top size of 1 mil. So like I said, media selection really is key for what you feed the mill. And another area is your disc spacer selection. This can change very much depending on your maintenance tasks. We have multiple size discs. And various spacers that really are done for maintenance concerns. So i.e., if you have a wear zone in a particular place, we can put a small diameter disc in. We can then spread out the spacers so you can remove zones of compaction and really find a solution to help extend the life of the parts. So those that don't know, this is the mill layout. This is an M5000 that's currently out in the plant. And I just wanted to run through some of the basic components that you might see on the mill. Typically, the feed is always fed on the non-drive ends, so the furthest end away from the motor. That feed will go through the mill where it will have a series of 8 discs similar to that previous diagram inside that mill. And then on the side towards the gearbox bearings, we'll have a discharge pipe. You can see the shaft bearings, gearbox, motor, they're the other key critical piece of equipment. And lastly, on that discharge line, you'll find that a line typically comes off and feeds a portion back to the feed tank. What happens there is we typically will recycle a portion of the discharge, normally designed around 20%, to maintain that level in the feed tank and reduce process stability, which actually corresponds to improvement in wear life within the parts. The development of that recycle was traditionally always while to include process stability, but it also had a significant influence on improving wear life. Now this is what the mill looks like. Like I said, we had that diagram before, but it's always better when you see it real. And this is exactly the same. You can see the discs, the rotor towards the end, and the series of discs along the shaft of the mill. One of the things that really is important, and especially from the maintenance side, is you'll see the rubbers are actually different colors. We have a red disc, which is a Duro 40, and a black disc, which is a Duro 60. Now, fundamentally, the difference between these is the compounds we put in. In areas that have basically are exposed to more heat, more aggressive grinding environments, we put a compound in those black discs effectively to move the heat away. by doing that, you get longer life, and particularly in those really aggressive, for example, MIG duties, you get a lot better performance at the mill. And typically we would optimize these particularly on each individual site with the selection. Now, the component layouts, this is the rotor. The rotor is pretty simple. We have different rotor fingers depending on the duties. So when I was talking about that pumping from the rotor, depending on the finger design, you have different efficiencies on that pumping action. We have the circular ones, which derate the rotor. We have the square ones, which is standard. And we have the rhomboidal ones, which you use for particularly low flow applications. Once the rotor fingers are selected, we put the rotor ring on, assemble it, and then slide it onto the shaft. One thing I would like to mention here is you can see that the shaft is keyed, which you'll see in a better picture in the next slide. So this is the shaft. The shaft is key. This is one of the benefits of doing it. Once maintenance on the mill. Once the discs and components are on, all you have to do is just slide it down the shaft, and it goes on well, easily, no complicated lifts. And once everything's on, you just put on the shaft end cap base plate, and the mill is pretty much good to go. With the discs, what we do is we have different spaces. We have shaft spaces, conical spaces, but one of the things that is really worth mentioning is we actually recycle disc hubs. Typically on an optimized maintenance program, it's possible to recycle the disc hubs, prep them into a new disc, and then by doing this, you can actually significantly reduce maintenance downtime with pre-prepared discs ready to go. Towards the end near the rotor, we have the displacement body screen. Typically maintenance at this end of the mill, since you have that rotor, keeping most of the media and the course towards the front of the mill. What that will do is effectively maintenance on here should be relatively less. Inside, we just wanted to go down and show some of the key components on the shell liner. This wavy sort of wear that you see here, this is actually normal and what you'd expect over time. As you can see, everything is lined within the mill, so everything is protected to extend the life to the maximum it can do. Now, we've quickly run through what the mill is, how it works, but we really want to talk about some of the exciting developments that have happened. And here, I just really want to reiterate that Glencore Technology is here. We continue to develop products, and we work all around the world. We are always there, keen to work with you, and we're always keen to ask for feedback. We always want to know what works, what doesn't work, and what we can do to improve effectively what we offer. So with this, we've actually brought a new set of mills online, and this is done specifically from feedback we got. And these mills have been the M7500, which is a mid-sized mill between 5,000 and 10,000. That was designed for particular applications where 5,000 wasn't enough, but no one really wanted to buy 10,000. They wanted something more bespoke for the application. We designed the 20,000 recently, which was built this year and should be commissioned by the end of the year. And we have designs for the 30,000 and 50,000. Just one thing I'll make a note on that is the 30,000 and 50,000 is a little bit more complex when you talk about maintenance items, because the components you actually have to ship in segments, not complete pieces. The mill design has had a significant overhaul. On the bottom left was the design that was pretty prominent around 2010. And as you can see, it's the elevated platform on the bottom left here and relatively high in the mill air. Sorry. What we've done is going out to market, we asked, what could we do better? And the first thing that normally comes back is they want us to, or we want to reduce cost and we want to reduce footprint. So what we did was reimagined the plant, had a bit of a discussion, and we worked out with a new ingenious way to try and really reduce the height, condense the footprint, and we were able to do that. And the thing that really drove that was we realized that you don't need to use gravity to discharge the mill for a maintenance cycle. What you can do is you can actually use that rotor. You know that rotor is inside the mill is doing that internal classification, but it's still pumping. If you have the media hopper close enough to the side of the mill, you can actually pump the media out to a hopper on the side, which is what we've done. And by doing that, you don't need to fill that void under the mill. And that significantly allows you to reduce concrete and steel. I think the estimates were it reduced at about 23 to 27%. We also turned around and were requested that people wanted removable rails. So we gave that option. We tied the mill into existing plant supplies, so you no longer had to supply the own groundwater tank. And really condensed everything by pushing everything together. And at the end of the day, by doing these changes, we've made a pretty competitive mill design where it sits in the footprint of an equal sized mill, and that's not even including the equal sized mill's powers auxiliary equipment as well. So it's a much more condensed plant that achieves what you want it to do. We've been doing R&D trials for 25 years on materials, and we continue to do so as we speak. We've tested many types of materials around the world, and we test these actually in a live mill. I got an example down here is when we test these materials via pizza flanges, where we have control samples across with new compounds. We then put them in the non-drive end of a mill, so where all that media sits, the more abrasive side. And then we monitor wear compared to our existing parts that we select. We've developed a database over 25 years of different material compounds. And what we've designed and what this has done is really developed and really brought a couple new products on, particularly those darker rubbers I alluded to earlier in the presentation. We also continually test new disc designs. So we do these on our lab scale mills. Any designs that seem and show promise, we actually take further to piloting, and then we take up through to full plant trials. And we have worked with clients on different applications and different discs, depending on what they want and their duties. And like I said, we're always keen for feedback. This particular example came from a particular site that identified that when they were running their trials on the different discs, that HD60s had a better wear life on the width of the disc, while the GD70 discs had a better life on the kidneys. And while we're discussing this, they just asked, couldn't you combine them both? So different rubber on the outside versus the kidney. And we said, sure. And so we sat down with them. We developed a new hybrid disc, dual compound, to try and really maximize the life. And we were able to provide these to the site for a trial. So really, like I'm saying, when we get feedback, we can push ourselves, we can get better, and we can develop better products for people that want to do specific things. And maintenance and monitoring. So maintenance is easy on an IsaMill. It's there are some very key maintenance attributes, but like I said, I personally think it's a lot safer. All major components are accessed on one level. The shell is on hydraulic rails, so it's really easy to access internal wear components. You don't have to take that shaft out. All the discs slide on, off with spacers, so maintenance is done relatively quick. There's no scaffolding, no working at heights, and lifts are not complicated. Downtime, typical plant availability is always greater than 97%. Maintenance is normally tied to another event within the plant, and downtime is relatively small. Assuming the mill is locked out, you can swap discs out, do inspections within 3 hours, shell liner 9 hours, gland rebuild less than 24 hours. Wear life is very dependent on the duty of the mill and where it is. But towards the front of the mill, you'd expect discs to last 3 to 6 months. Towards the end of the mill, where you're away from the media, lasts about 24 months. The shell liner should last about a year. So what I'm really saying is maintenance can always be optimized through different systems, but maintenance is easy with an IsaMill, as the slide is indicating. Now, I'd like to pass it on to Lauren to show you this quick video. But this quick little video shows you exactly how to do the maintenance and all the work involved. If I can pass it on to Lauren. Thank you.
Check with operations that the mill has been through the correct flushing cycle. Isolate and lock out the IsaMill motor and the feed pump motor, as well as the gland sealed water and the gland flushing water supplies. Activate the mill's scuttle valve and empty the remaining contents, if any, into the media hopper. Disconnect the mill feed line, flush water line, valve air line and instrument connections. Unbolt the mill slurry feed pipe and swing or lift the pipeline assembly away. Move the hydraulic power pack to the mill adjacent to the quick release hydraulic connections. Connect the hydraulic power pack hoses to the mill. Remove the drive and flange bolts. Ensure that all personnel stand clear of the IsaMill shell. Once everyone is clear of the area, it's safe to open up the IsaMill shell. Once the shell is open, install the safety pin. Pull the shell away from the drive and flange with the hydraulic power pack and give the mill internals a thorough hosing if required. Inspect the mill internal components and record component dimensions on the routine maintenance inspection sheet. Record the measurements of the shell liner as detailed on the IMIS. Measure and record the minimum rubber thicknesses of the flange liners. Inspect the rotor and discharge ring for wear. If the shell liner wear dictates, then rotate or replace the shell liner as required. Measure grinding disc dimensions and record by marking dimensions on the discs and in the log sheet. Replace discs that are worn beyond the point of reuse. The disc hubs must be removed from any discs that are replaced. It's good practice to prepare new discs with the removed hubs before the next maintenance opportunity. Rotate the position of worn discs that can be reused. For example, disc number X will be replaced. Disc number Y will be reinstalled and into position Z. Take a full photographic record of all wear components. Close the IsaMill shell using the hydraulic power pack. Uncouple the hydraulic cylinders from the shell and retract the cylinders fully. Store the power pack as per the procedure. Reconnect the flushing water line. Lift the inlet pipe assembly into place and bolt it to the mill. Connect the air line and instrument cables. And finally, remove the isolations from the various services. The inspection involves establishing checks and measurements of all IsaMill parts to interpret the wear and functionality of all the individual parts.
Thank you for that. So as you can see, very, very simple to do basic maintenance on the IsaMill. Now I wanted to touch on some of the new monitoring tools that we actually use, and there is a bit of ongoing R&D at the moment, and one of the areas is acoustics. We have developed a acoustic analyzer that can sit on the side of the mill. Any IsaMill that now produces actually has these predetermined sensor drill slots actually drilled into the side of the shell, and it's seen exactly like you can see in the picture on the right. What this does is it's an acoustic accelerometer that actually sits on the mill shell liner. And what it does is it interprets the stress waves as the media and slurry hits the liner, and that gives off a signal. When that signal changes, it actually reflects a change in wear pattern and change in operation. And what that can do is tell you where your media is positioned along the mill, but it can also tell you and show you predict a liner failure. We've published this at KCGM back in 2018, that the change in acoustic frequency as the media hit the shell predicted a shell liner failure 24 hours prior to actually occurring. We are commercializing this technology, and we can use this tomorrow to predict wear rates, but We're also taking it further and actually using it for particle size analysis as well, which we are currently doing through various stages of R&D at the moment. So another area that is part of the maintenance cycle is actually thermal surveys. Thermal surveys is something that we would recommend, particularly in the mornings, just for sunrises. But what we do here is it's done specifically to try and look for potential areas of media compaction. Media compaction is when you hit a zone within the mill and the media no longer behaves that fluidized behavior. And as it does that, it basically starts digging into the mill shell, and that actually starts to create heat. That heat can be viewed from outside the mill. If you do thermal surveys, you can actually point and see where a lot of that heat is being generated. And we've developed a general rule of thumb that if you look at the entire mill and break it up into 16 points on a survey, if you see a temperature change of 10 degrees over the entire mill shell length, you'll know that you potentially have a compaction issue. Or if you see various changes in temperatures greater than 5 degrees between the individual points on the shell, may indicate a compaction issue. This is something that we're trying to encourage more for predictive maintenance, particularly in those duties such as MIG grinding duties or duties where you see highly aggressive wear. And now I'd like to pass on to the panel discussion. I hope people have been writing down questions, but I'd like to pass it along back to Scott. Thank you.
Yeah, thanks very much, John. Very informative presentation. Now we'll open it up to the floor of our panel. So our panelists, like I said, is kind of the brains of the operation. I don't know if you can share that slide again, Jan, because it kind of had nice pictures of everyone. So Tim Shea is the manager of projects and engineering, 30 years in the mining industry, and he's been leading our aftermarket and engineering division since 2006. Lily Sanchez is our aftermarket engineer. She's a certified auditor and Six Sigma practitioner. She uses analysis to increase efficiency and reduce waste in processes. Adriana, I'm not sure if he's on. Unfortunately, they're doing that power sharing stuff in South Africa today, so I think he's a victim of that, but nonetheless a great resource for us. And some of you in North America I know have probably talked to him before. He's been the service manager since 2010. And lastly, Roy Stevenson, electrical and instrumentation engineer within the mechanical engineering team, 33 years in mining. So lots of good questions and lots of good experience. So hopefully we have lots of good questions for this panel. So again, just want to summarize, if we don't get to everyone's question, we'll definitely respond by email at the end. So the first one, I'll let Tim and Lily flip a coin, but I know we experienced this at a mine in British Columbia recently. What is the expected life of the gearbox, and when should a site budget to have it replaced? And maybe along that line, what are the lead times with these gearboxes? So maybe pre-COVID, they were quick and easy to find, but do you notice that they're getting longer and harder to source?
Thanks, Scott. The gearboxes are designed for any gearbox, not just IsaMill gearboxes, but any gearbox is designed largely around its bearing life. So the bearing life in our gearboxes is nominally a 10-year bearing life. So you can expect, if your gearbox is well maintained, so the oil is kept clean, it's changed at the regular maintenance intervals, you can expect 10 years life out of a gearbox. Now, on some sites, we have seen lives less than that. On many sites, including some of our own sites, we've seen far longer lives than that. It really does depend on how the gearboxes are treated and the loads and that type of thing. But a 10-year life is a reasonable expectation. Now, the bigger gearboxes, so on our M5000s, M10000s, M20000s, M15000s, the time to build one of those gearboxes is about 9 months. So it's one of the reasons we really recommend that the sites that are operating these gearboxes do a risk analysis and assess whether they can afford to have a loss of production of several months. Depending on the failure mechanism, so if you have if it's just a bearing, then it's a relatively quick repair to do on site. You can probably do a bearing change in under 2 days. But if it was a gear set, it might take several months to produce the gear set before you could then do a change. The change itself could be done quite quickly, but it will take an extended period to get those parts. So what we do when we have a new site we're working with, we'll work with them about looking at their risk appetite and seeing what sort of risk they're prepared to take and balance that against the cost of holding spare parts. So I hope that answers the question, Scott.
That does it. And the next one, kind of along that line for Lily, is so how can a client get us to site to do a mechanical audit? And again, I guess this is more specific to this market area over here.
Sure. Well, I think we already, what is it, 2 years since the world changed due to COVID, but slowly you can see that travel and, site visits are a possibility again. We went through a period of time not too long ago where it was a bit unsure, uncertain, but now, yes, it starts with me. So if you would like us to attend site, do a mechanical audit, I am the one that would be putting a proposal for you. So it would depend, on your timeline, on the location of the site, of course, and usually Adrian or Johan would be available to go to your site and perform the work. So yeah, just reach out, and we'll get the conversation started. It's just a matter of agreeing on a point in time, because you have to. Ideally, you would like to plan a little bit around it because you want your spares on site, right? You don't want to risk oh yeah, you need to change that. Oops, we have nothing in stock. It requires a bit of planning, and I am more than happy to assist with that.
Okay, thanks. And we'll set.
Scott, it's probably worth noting that Roy, Adrian, Johan, myself, we've actually worked on the majority of those sites in North America, so we are quite experienced with those sites, and we can provide really good support by telephone or by email to those sites. So a place to start is really by sending us an email or ringing one of us, and we can provide really good support that way, which is almost instantaneous. But equally, we've worked on the majority of the sites in North America, so if that's what's needed, we can easily do that.
Yeah, for sure. I mean, for instances where you have problems or questions that are specific, of course, the whole team is available to help you. A mechanical audit is more about, for example, it involves some training. So some sites can have a high turnover of staff. So, it has happened that sometimes sites would really benefit from, some of our experts to spend some time on site, train your staff, review your processes. They look at you doing your maintenance, they look at everything, and they basically reset the maintenance program of your IsaMill. That's like a little bit the difference between specific issues with your maintenance and your IsaMill, and a more comprehensive overview of your maintenance program of the IsaMill.
Okay, thanks very much. And we'll send everyone's contact information out with the question. So we do have a live question here, and I'm going to put this to Roy. If anyone else has any insights, jump in. But this is from the Eleanor operation. 2 questions related to efficiency and control of the IsaMill. So I guess we'll start kind of with efficiency and then go to the control. Currently, the feed pump box level is controlled with a recirculation loop. The 6-inch plug valve that controls recirculation experiences stiction and operates inaccurately between 0 and 10%. Do you have any control advice regarding this?
Yeah, stiction is a yeah. No, I'd have to look at that because it all depends on what your flows and where your pipe work is, as in where the discharge, the feed and the discharge to the valve, and also the pressure, the air pressure on the valve, etc. If they can send me all the details on the pipeline and the pressure, the air pressure they're using, the valve they're using, I'd say they're using probably Wide-Dart. That's our usual recycle valve. So they can send me all that information, and then we can have a look at it.
Yeah, no problem. We'll send you the contact details, and then the second question, either for yourself or maybe Jan doing the SIG plots. But when we're doing the lab tests, is it better to aim for the maximum kilowatt achievable, or lower the target but with a higher percent recirculation and flow rates? The question is based on in terms of efficiency and pumping viscosity, which at this operation is a bottleneck.
Happy to jump on this one, Roy. With the lab tests, typically the signature plot is designed to determine a specific energy. Once we have that specific energy in the IsaMill design process, we'll try to target that, design the mill so that will be easily achievable per the initial design conditions that were supplied to us. As with any operation, typically we want to try and step up throughput as the life of the asset goes on. And from this question here, in my personal opinion, it's probably better to aim to try and increase the power draw, because that's typically corresponded to plant increases in throughput, and then try to develop strategies to push the existing equipment to the higher limit. And there are things you can do to try and get around that. I know with high viscosity sites, there's forms of dilution, potential viscosity modifiers, and reviewing the plant layout. I'm happy to discuss this further with you guys offline, if that's okay.
Yeah, thanks, Jan. And what we're seeing a lot is operations pushing the limits of, forcing tons and really running these machines to their limits. So this is kind of for anyone. Does anyone have any tips for longer operation time and less parts replacements?
Yeah.
Sorry, you go, Lily.
Oh, but I was just going to say, the longer you run your IsaMill, the less chance you have to, for example, as per the video showed, flip, switch, swap your discs or your shell liners. So there is a fine balance there between, and this is the decision we're more than happy to assist you with, as to how long my campaign can be. Either aiming at maximizing the wear life of the components, that will mean generally a bit shorter campaigns, versus leaving the IsaMill, run longer, and just, leave it with the fact that when you open up the machine, you will see the wear that you have not seen before, and most likely you will have to just, make more changes, new components. So that's just a trade-off. I don't know what you were going to say, Tim, about it, because that's what I've seen.
Yeah. No, thanks, Lily. That's true. I think, Scott, one of the things I'd say is work with us to optimize the process conditions, optimize the approach to maintenance. So there's many things we can do to adjust the mills to suit the site conditions. So during Jan's presentation, he mentioned that we can change the size or the position of the discs. We can change the rotor fingers. We can change the wear compounds that are used inside the mill. So there's a number of things we can do to actually optimize the mill arrangement to suit the specific site conditions. Even adjusting the process conditions. I think Jan mentioned just a couple of minutes ago that the viscosity can have an impact. The slurry density can have an impact. So if you work with the guys that have done it on many different sites, We can optimize the process conditions. We can also optimize the maintenance configuration of the mills. And then, as Ludwig said, once we've done that, we can work with the sites to come up with the best approach to a maintenance campaign.
Roy, do you have anything else to add? Just kind of on tips for longer operation, or?
Yeah, a good maintenance program is always the answer. A lot of sites, first thing they cut is maintenance, which is a fairly big mistake. But there is such a thing as over maintenance. You really need to go through your maintenance and look at your equipment, look at the manufacturer's recommendations. But that's pretty generic. You need, with any maintenance program, you need to start with a lot of interventions, and then work your way out until you find a position where you've got your maintenance is good. You're not having breakdowns. Like I say, there is you're not doing yourself any favors by over maintaining. You're actually that's where a company will look and say the costs are too high. We have to cut maintenance. So yeah, you have to be pretty smart about it.
Yeah, thanks. And along that lines, there's been also coming out of COVID a lot of changeovers and with people. So like Tim said, you guys have been involved in the Indaco, the Mount Milligan days, et cetera, and there's a lot of knowledge there at Gibraltar. But I think it's good that we work with these sites like we are to support them. And this is another live question coming in now from Mount Milligan. And I'll pass this one to Jan, but they have 2 IsaMills on site. One of the mills was down for several weeks due to a failure of a shaft in the gearbox. And while that mill was down, the Met team noticed really no difference in recovery during that period. So would it be possible to get or support them with the operating parameters audit and make sure that they're operating the mill for maximum efficiency?
Happy to help on this one, Scott. This is a really, really good question. Ultimately, it's very, very hard to make a conclusion on how a plant is performing without any tools. But in short, we're happy to help audit, look how your mill's running, see what we can do better to work with you. But with regards to how the plant behaved during a period where that mill may have been offline, it's very hard to tell without a lot more data. And like I said, I'm happy to have a chat with you offline and we can talk this further. But it could be due to many things. For example, process conditions, less throughput, or mineralogy. So yeah, we'll take this and discuss this further offline if that's okay.
Yeah, okay, thanks, Jan. And we are getting close to the end. We have about 8 minutes left. So one of the exciting things that I'm not really allowed to talk about is our work that we're looking at coarse grinding opportunities. So along that question is, as we see mills over here getting into more coarser grind than ultra fine regrind applications. So Tim, do you have an idea the maintenance cost, how it varies between fine and ultra fine regrind applications?
That's a really tough question, Scott.
Okay.
It is dependent on a great many things. I'll give you an example. So we do some grinding in a gold operation in Australia, where the mill is on a 13-week maintenance interval. So they run the mill for 13 weeks, open it, rotate some discs, put it back to work for another 13 weeks. And that's a relatively coarse feed. We've got mills with similar size feed in the platinum industry that go 3 weeks before they have to do the same thing. So it's very dependent on the mineralogy. It's very dependent on the ore types. So it does depend. But a rule of thumb is that the coarser it gets, the more aggressive is the wear inside the mill. Now there's things we can do. We can tune our wear components. So if we have a very stable process with very few sort of deviations in the process conditions, we can really finely tune the wear compounds to give the best life. In different operations where we might have variability in the process, and there's lots, let's be real, this is the real life that happens, we can go to a more durable or more resilient sort of wear compound. It may not give you quite the wear life, however, it can handle aberrations in the process. So there is things you can do. But unfortunately, when you're dealing with coarser feeds, that means the particles that you're dealing with are heavier, so they have more energy when they're moving, and they're bigger. When you break them, you get sharper edges, so you have no choice. Bigger feeds lead to faster wear.
I have another one. Maybe it sounds silly, but you'll be surprised how many components don't get to see the life that they could due to little things like O-rings. And I hope this is not too obvious of an information, but honestly, if you don't remember or don't have access to your spares list, or you're confused about what O-rings it was, part numbers, whatever, just reach out. The service team will be able to give you the information that you need, so you have the corresponding O-rings and plugs and stuff in place, so that you don't have media and slurry creeping in where it shouldn't be, because you either forgot the O-ring or have an ill-sized one. Same.
Yeah, that's a great point leading into our next question. And maybe Lily, you can start, and Tim and Roy, if you have anything else to add. But why would an operation get slurry onto the shaft, making removal of the components difficult?
Yes. Well, as far as I understand, I'm sad that Adrian is not online. So it starts with the fit. So it starts when you fit your shaft end cap and your faceplate on, because that torque and those bolts are the ones that are going to compress and leave all of the components on the shaft in place. So if you are under or over torquing that one, it's going to leave you vulnerable. You also have some, again, O-rings in between, on your shaft spacers and your disc cups and plugs that could if they're worn out, if they're not there, whatever it is, it could also get in through there. Normal wear. So if your component, if your shaft spacer, which is a cylinder, when it's new, has worn out, or your disc cup also. So if you lose that material and you don't make a maintenance decision about it, if you run it that way, just that extra gap there is going to make it easy for slurry to make its home there. It will get in if you can. And so those are the three things that I can think of. On the drive end flange assembly, it will be then the fit from your liner to your, you call it screen in some sites, we call it discharge ring. So the rubber components. So that you always want to make sure that they're fitted as nicely together as possible. I don't know, Tim, if you wanna, Troy or Roy, wanna add something there that I missed?
Yeah, no, I think you've covered it, Lily. I would add though that the way that we seal the components along the shaft is with O-rings. Now the tolerances, the way that an O-ring works relies on the rubber O-ring being compressed and sealing. As the rubber ages, it hardens and it deforms to a preset shape. It becomes a little bit less elastic. So one of the things we found is that if we leave O-rings in place for several years, they get hard and then they don't seal properly. So we would recommend changing the O-rings on the shaft much more regularly than that. In fact, one of the issues we've got, so on some of our mills in fine grind applications, the discs at the non-drive end, at the discharge end, the drive end, are lasting years. So the natural instinct of a maintenance person is not to touch the, never to disturb them. But the problem is that the whole time the O-ring is getting harder and is taking a set into the shape. So we recommend at least once a year you replace the O-rings on the shaft so that they're fresh. The other thing to think about is that the tolerances between the components on the shaft is reasonably tight, so cleanliness is important. If you have a bead of media between the components, it means that they won't close up properly and your O-ring does not get a chance to seal properly. So all of those things lead to the seal not being effective and slurry being allowed to get between the components and down onto the shaft. And that's a nightmare because it extends the time it takes to do the maintenance. It's much harder to do. There's a risk of damage to components. So yeah, for the sake of some relatively inexpensive O-rings, it's much better to change it out. You're on mute, Scott.
Thanks. We're getting some good questions in, but unfortunately we have 1 minute left. So I'll just wrap it up with our presenter, Jan. And again, we'll email everyone these questions with answers. So what is the product size range the IsaMills usually handle? Can somebody assume an IsaMill runs at a high tip speed and thus more specialized in fine grinding, say 20 microns or less? And how can that product size be adjusted? And you have about a minute left.
No problem. Sorry. No problem. Thanks, Scott. That's a very good question. When the IsaMill was originally developed, it was originally developed to target the ultrafine grinding range of 7 microns. And the function of that was your media selected. As the mill has developed and more ceramic media has come available on the market, we did a big extensive campaign back in 2006 using 6mm ceramic media at the time. And using that, we found that the mill was comfortably able to take feeds up to 400, 500 microns with a top size of 1 mil. What you feed the mill is pretty much derived on your media selected. As Scott alluded to earlier, we're looking at trying to move into coarser grinding applications. More larger medias exist up to 10, 12 mil. So as we use these larger mills, we expect the product size range of the IsaMill to increase correspondingly. So if you're trying to adjust what you're feeding the mill, media is the main thing you would adjust, but the range of the IsaMill is actually a lot bigger than you would originally think, depending on how it's designed. So I hope that helped.
Yeah, thanks very much. And with that, we're running out of time. So thank you to everyone who attended today. I want to also thank the panelists and Jan for a great presentation. If you have any questions, you can email us isamill@glencore.com.au. You can email myself, Lily, Tim, Roy, or Jan. Also, I encourage you to follow us on LinkedIn, but also visit our website. One thing we didn't really push a lot today is our pretty cool calculator. So if you have questions on sizings and things like that, you can run it through our online calculator on the website and it generates a mill sizing, etc. We also have all of our papers and presentations on the website. So thank you once again for attending today, and we will follow up early next week with the questions, link to the presentation, as well as all the contact information for Lily, Tim, Roy, Jan, and myself. So thank you very much.